If you haven't subscribed, ensure you do so. A baseball hits a car, breaking its window and triggering its alarm, which sounds at a frequency of 1250 Hz. What frequency is heard by a boy on a bicycle riding away from the car at 6.50 meters per second? So this is the speed. So this is the car here, which is stationary. Then this is the boy here on a bicycle. So imagine a baseball hits the car, which has and the alarm is triggered. So this is the scenario that has been shown here. This is the car that is stationary. Then the boy is moving to this direction, and it's at this speed. So if a car or a truck is moving while its horn is blowing, the frequency of the sound you hear is higher as the vehicle approaches you and lower as it moves away from you. This phenomenon is one example of Doppler effect, which is it was named after the Austrian physicist Christian Doppler. So um, So this same effect is heard if you are on a motorcycle and the horn is stationary. The frequency is higher as you approach the source and lower as you move away. So although the Doppler effect is most often associated with sound, it's common to all waves, including light. So this is the scenario we have here. Right. So in this scenario, we are going to use is what we call general case. So the formulas that we will be using it for the general case. So this is the formula, and this is the formula, which is it's just the same formula but being expressed in different forms. So when both the source and the observer are in motion relative to Earth, equations this one. So these equations, they are used. All right. So in this expression, the signs for the values substituted for VO and VS depend on the direction of the velocity. When the observer moves towards the source, a positive speed is substituted for VO. Then when the observer moves away from the source, a negative speed is substituted for VO. Similarly, a positive speed is substituted for VS when the source moves towards the observer. A negative speed when the source moves away from the observer. So it is also important to note that choosing incorrect signs is the most common mistakes made in working a Doppler effect problem like the one we have at hand. So the following rules may be helpful. The word toward is associated with an increase in the observed velocity. The words away are associated with a decrease in the observed frequency. So let's also look at this important information that we have here. So in our question, they have not mentioned the speed of sound in air. So we are saying unless otherwise specified, assume the speed of sound in air is 343 meters per second. its value at an air temperature 20.0 degrees Celsius. At any other Celsius temperature, the speed of sound in air is described by the equation 14.4, which is this equation. So if they have not specified the speed of sound in air, then we have to use 343. But if they have to if they have specified the, let's say, the temperature, then sorry, not this temperature, but if they've specified, let's say, 25 degrees Celsius, then we have to use this formula to find the speed of sound in air, where V is in meters per second and T is temperature in degrees Celsius. Right. So at this point, let's now look at our problem. So we are saying we are going to use this formula for the general case. So FO, which is frequency by the observer over speed of sound in air plus velocity of the observer, is equal to the frequency by the source and the over speed of sound in air minus velocity of the source. So as we have mentioned, we want to find the frequency of by the observer. So the speed of sound we've mentioned to in air to be 343 meters per second, then plus then the speed of the speed of the speed the observer is moving at, we said it's 6.5 meters per second, but we are putting a negative because this observer is moving away from the source of sound, so it becomes negative, and when you multiply a positive and negative, you are getting a negative. So this side, Fs, which is a frequency of the source, over 343 minus 0 meters. So 0 meters per second, this, since the observer is stationary, then since the source of sound is stationary, so it's 0 meters per second. So this is when we solve this, that we are getting this here, right? So this is the expression we got from the previous slide. So when you cross multiply here, you are getting 343 meters per second. FO, which is a frequency by the observer, is equal to 336.5 meters per second multiplied by frequency by the source, of sound. So here we are seeing that the frequency by the source, it's 1250. So when we multiply this, we are getting 420,625 meters per second multiplied by the haze, like that. So we want to remain with the frequency by the observer. So we divide both sides by 343, then we are getting our frequency to be 1226.311953 hertz. So this is the frequency we are getting. So this frequency can be written into 3 significant figures as that, or in standard scientific notation, to be like that. So at this point, we are done answering what this question required us to do. Thanks for watching. Remember to subscribe to our YouTube channel.